Hello and welcome back to Physics for the 21st Century. My name is Greg Perugini and today's topic is circular motion. We're going to be introducing this topic. We're going to talk a lot more about it in a subsequent topic. But for now, you need to know that if I am moving around the curve, I have a velocity around the curve. Of course, in terms of Newton's first law, I want to continue on in this direction. But there is a acceleration, centripetal acceleration, towards the center. Always center seeking. And we can define that as r velocity squared over r. So obviously, the acceleration centripetal depends upon how fast I am going and the radius, this being the radius of our curve. So we can relate circular motion to tangential motion in terms of radians, and we're going to mark that as radians. And in terms of rads per second, radians per second, we're going to define that as an omega. Centripetal acceleration is just simply, or I should say angular acceleration would be acceleration divided by r, or in this case, centripetal acceleration I'm going to define as an alpha times r. We're going to be using this in kinematics later, and but for this particular topic, you're going to need to do some dimension analysis. You're going to need to understand that. Also, keep in mind that what we're talking about is an acceleration, and of course, if we're accelerating around a curve, we still have F equal ma. So if I want the force of that centripetal acceleration, it's mv squared over r. Just multiplying the m in here. So if we look at our curve, you can see here is defined the radius of the curve. This is an omega and this is alpha. And of course, omega is the change of the radians over time, rads per second. And as I said before, angular acceleration is rads per second squared. I can get the length of this subtend, called a subtend, I can get that length, this area here, or I should say this line here, by taking the radians, and there's 2 pi radians for every 360 degrees, and multiplying it by the radius from the center of the circle out, being the radius. Let's look at a couple of problems that you might be getting in terms of that. So you can just simply see how with acceleration equal v squared over r, how I can solve that type of equation. I also want to define something called the period. We're going to say period is t, and that's going to be in seconds. It is how many seconds it takes to do one revolution. And I can define my angular speed in rads per second, knowing that there are 2 pi rads, as you can see in the circle, for every one revolution. And as I said, this will involve some dimension analysis for you probably. So, knowing that, let's do a quick example here. Let's do a quick example. I have a centrifuge. A centrifuge. And that centrifuge is going at 3,000 RPM. Common term in engineering, RPM. What is its angular velocity? Well, if we know that it does 3,000 revolutions for every 1 minute, doing our dimension analysis, we know 1 minute is equal to 60 seconds, and that there are 2 pi rad for every 1 revolution. You see what happens here. The revolutions cancel, the minutes cancel, and I'm just left with rads per second, which is what omega is. So if I do the math on that, 3,000 times 2 times pi, and then divide it by 60, you'll get 628 rads per second. Fairly straightforward. So know this particular conversion factor, and you should have no problem with these type of problems. Now once I know omega, just keep in mind that there is an equivalency with omega in that velocity is equal to omega times the radius. So I can get the velocity around this curve in terms of tangential velocity, much like we did in the previous slide. Let's look at that centripetal acceleration again. Centripetal acceleration is equal to v squared over r. So if I am on a curve and the radius of that curve is 8 meters, let's say, and I want to feel an acceleration here, I'm on this edge, I want to feel the acceleration here at 7 meters per second squared. Not quite a gravity, but I want to feel that. How fast do I need to go? Around that curve. Well, using this equation, we want to feel an acceleration pushing us against the edge. Now, that's that fictitious force, that centrifugal force, as we are trying to stay on the curve going straight. And of course, the curve is bending around. So that's sort of throwing us along the side. So if we look at this equation here, I want 7 equal to velocity squared over whatever the radius is, 8. So to get 7 meters per second squared feel on this edge, I simply have v squared equal to 56. Okay? So you can see how fast I have to go, roughly square root of 56. So that's the type of problem you would need to solve for in terms of centripetal acceleration. Also, we need to know the frequency. That's another thing you will need to know for this chapter. The frequency around the curve. frequency is equal to 1 over the period. So if it takes me 30 seconds to go 1 revolution, my period is equal to 30 seconds, and my frequency, which is in hertz, is equal to 1 over 30. Fairly straightforward, easy topic here. So have your conversion equations ready. Understand your conversion factors and be comfortable with your dimension analysis. And practice problems online and in the book as well. Good luck.